thank you to Andrew and also thank you to Bill for talking about the hardware stack and also a bit about GroqFlow and how to get set up on the ALCF rack. I'm going to be talking about the general software stack, the Groqware suite, and how best to interface with it. And Bill's kind of alluded to it before using GroqFlow. And in this session, I'm going to talk at a very high level about our software stack, how to use GroqFlow, the best practices, and also go through some hands-on examples with some code. So let's just kind of get into it. Like I mentioned before, we're going to go through a high-level overview, talk about GroqFlow, and once we've ported models with GroqFlow, I'm going to talk about MLAgility, which is our open source benchmarking tool, which we use to benchmark models that we've ported. We benchmark them on the Groq system and also on other third-party vendors. So for example, the NVIDIA GPUs and also CPUs as well. All right, now let's talk about the Groqware suite. Now, to get something like a large language model running at 1,000 tokens per second, we need great hardware, but also we need software to go alongside it. We need both of these stories to come together. And on the Groq side, the system software kind of looks like this. If we're looking at an application, for example, a GPT-2 type model, it could be something in HPC as well. This is the flow we'd go through in getting it ported, compiled, and also running on the Groq system. So let's start with an application, for example, in PyTorch. It could be in any other kind of framework that you're using, for example, Keras, TensorFlow, so on and so forth. I'm just going to use PyTorch as my default. The way this application goes through our software stack is as follows. We start with the application, we reduce it or we translate it into ONNX. And ONNX stands for Open Neural Network Exchange. It's designed to be some sort of a standard which allows you to interrupt between these machine learning frameworks. So for example, PyTorch and TensorFlow. Where PyTorch has thousands of operations, ONNX has a much smaller subset on the order of 100. And this allows hardware vendors to target a smaller subset of operations on their specific hardware. Now, once we have an ONNX model, this is then passed into our compiler. And Bill was mentioning this before, but we also have another front end. It's the direct torch importer. So this kind of bypasses ONNX altogether. And for those of you interested, we have this in our documentation. And I think you can contact ANL to get your hands on that. But going back to our flow, let's say you have an ONNX model, you pass it into our compiler. Once it goes through the compiler, it's kind of broken down into even more steps, the front end, the middle end, and the back end. And tomorrow, Philip Larson's going to talk about this in a lot more detail. But kind of on a high level overview, what's going on is we translate this ONNX IR into our own intermediate representation. We call it G10. And for those of you who've used PyTorch, that may sound familiar. It's very similar to A10, which is PyTorch's namespace. Once that's done, we go through the middle end where we kind of partition and also shard the model across chips. And then it's then scheduled. If you remember Andrew's section, we talked about how everything was deterministic and at each cycle, we know where all the data is and where it's going to go to. Once we've passed through the compiler, what we emit is ALN assembly, which is text readable assembly code. It tells us everything about the scheduling and where the data is going to be at every single cycle. If you've ever played around with GCC or G++, it's very similar to the assembly generated from that. And now once we have the assembly, we pass it through the assembler and get a binary at the end of it. The binary we call an IOP, which stands for Input Output Program, an IOP. And then we have an executable and we want to run it. We interface with the Groq runtime to run it. And that's kind of the end of it. We can target different topologies. We can target a single chip. We can target 2 chips, 4 chips, a node, even up to a rack, and so on and so forth. So on the ALCF right now, you have a single rack. A rack has 8 nodes and 1 backup node. So you have up to 72 cards to play around with. So this is the interface you use to kind of port your applications. And you can go through all of these steps stage by stage, or you can use our preferred method, which is GroqFlow. You can kind of see that on the left-hand side. This is almost like a highway abstracting everything away. And it gets you a binary, an IOP, which can then run on whatever kind of topology you want out of the box. All right. Now, once you have a running executable, you kind of want to benchmark it. And for that, we have our own open source benchmarking tool called MLAgility. The reason we work with MLAgility is because we want to make our benchmarking completely transparent. We want you to understand how we come up with our numbers when we say we do, 1 order of magnitude, 2 orders of magnitude better than the competition. All of this is open source. It's on our public GitHub page, MLAgility, under our Groq page. You can have a look. You can see how we do our benchmarking. You can see all the models we've done benchmarking on too. And all of that is also public on our Hugging Face page. I'm just going to show that real quick. A lot of this is still work in progress, so just bear that in mind. I'm still working on adding more models. Internally, we've got around 1,000 models running, but as things stand, let's say on this page, you can see we've tested with GroqFlow 168 models. All of them bypass, well, they successfully pass through the ONIX steps. And then once it gets down to Groq, most of them go through. And this has actually improved recently because of compiler improvements. We tend to get much, much better which each PR of our compiler. You can see kind of, well, let me choose a different baseline for those models. Let's choose maybe NVIDIA. We do quite a lot better than them. Like I mentioned, all of this is public. I think we'll share the link later on as well. So if you wanted to have a look, maybe you were interested in porting a model to Groq and wanted to see how well we perform, all of this is there. And if you wanted to see the benchmarking methodology, which I'll describe in a bit more detail later, you can also go through the code. All right, now let me go back to talking about benchmarking and maybe about the architecture of MLAgility. So like I mentioned before, we can benchmark a variety of models on Groq and also on other hardware. We can also benchmark with different runtime. So for example, this flow looks very similar to what you see on the right-hand side, this kind of system architecture overview. As input, we have models. It's passed into our benchit CLI. You just kind of call benchit on these files, which I'll show you how to specify. And you can choose a target. So the target includes the runtime. So this could be an optimized runtime, for example, TensorRT, or it could be ONIX runtime GPU or like the vanilla PyTorch runtime. And that could target, for example, the CPU, the GPU, or you can use GroqFlow to target the LPU. All right. So as a recap, we port models with GroqFlow and we benchmark them with MLAgility. That's all there is to it. And in the next section, I'm going to talk about how we actually port models with GroqFlow and go through some best practices and also some examples. But before that, maybe I'm just going to look through the chat and see if there's any questions.
There is one question. I'm not sure what's being referred to. This metric on MLAgility reflects only inference, correct? Question in relation to what you showed, which I'm assuming is the MLAgility Hugging Face space.
Yeah, exactly. So at Groq, we're really targeting inference, low latency inference, deterministic low latency inference. So all those benchmarks are regarding inference. Yeah. If you look at, let's say, MLPerf benchmarks, which you might see out there, that includes training and also inference, I believe. But MLAgility, it's just targeting inference. Yeah, exactly. I think your name is Sharma. Yeah, that's right. Yeah, cool. And let me just go to the next section. We're going to port models with GroqFlow. So in this section, I'm going to talk about what GroqFlow is. Bill kind of talked about this as well. He kind of stole a bit of my thunder, but that's completely fine. We'll just skip the setup stages, and we're going to go right into best practices examples, so you can kind of get your hands dirty and port your own models. How to debug GroqFlow if anything were to go wrong. We're also going to unwrap GroqFlow. If you remember the diagram I showed before, GroqFlow is a highway extracting all of these components, and I'm going to show you how you can actually interface with each of these components in a real life situation in a ResNet 50 example. That's going to go on in a bit later. All right, so you've already seen this, but GroqFlow is extremely simple to interface with. You can do this in just 3 steps. Number one, you get your model, you instantiate your model. So for example, here, we grab the GPT-2 model from the transformers library from Hugging Face. We instantiate it with its configuration. Number two, we grab some inputs. And in this case, we're representing the inputs as a dictionary. For those of you familiar with Onyx Runtime, this is kind of how you interface with Onyx Runtime. You pass in a dictionary as input. And with PyTorch as well, you can kind of unpack this dictionary and it works the same. But something for you to keep in mind, we'd like you to represent your inputs as a dictionary, representing a name for each input and the data type for each input as well. And another best practice we like to look into is we want to specify the right sizes for your inputs. So we talked about how the Groq system was deterministic, and this kind of works right now only when the input sizes and all the sizes throughout your graph, your compute graph, are static. If let's say once you have an input size of 1 and the next time you have an input size of 20, things might, your timing might go off. So what we do is we fix an input size, and for anything less than that, you just zero pad it. All right. After that, you just call the Groqit function call, you pass your model, you pass your inputs into it, and it goes through all of those steps. So I'm just going to reiterate that. It converts to Onyx, it optimizes your Onyx file, it checks for support. And when it says checks for support, it checks for support within our Groq compiler, converts to float 16, compiles, assembles. And now once you've got your IOP, you want to run it on the inputs. And you just unpack your inputs, passing it to Groq model over here. And that's it. So what if things don't go as planned? There are 1, 2, 3, 4, 5, 6 stages in the pipeline over here. That could be failures in any one of these 6 stages. Now, we try and do our best, and we mention how to follow up if something were to go wrong. So for example, if there's a lack of op support, we prompt you to contact us so we can deal with it. However, I'm going to talk in the rest of the section if let's say we had issues with, for example, converting to float 16 or converting to Onyx, how you might want to, let's say, handle it and fix it. And I'll go through some examples, and I'll also post them, and I think in a GitHub repo after this too. All right, so that's going through GroqFlow. I'm just going to talk about this again, talking about the highlights of GroqFlow and the features that we have. So we pass in the model, we pass in the inputs. The best practice is to specify a static input size and zero pad. So for example, if we're using, let's say, a natural language processing type model, we wouldn't want to just pass in inputs like this. We'd want to pass in a max sequence length too. Another area where this can crop up as well is also with graph neural networks. For example, when you're working with graphs which may have different numbers of nodes and edge features, what we want to do is just specify a fixed, let's say, edge index and also node feature dimension. And for all of the inputs that you pass into it, just zero pad if it's smaller than that. All right, and in GroqFlow, you can mention the number of chips you want to target as well. You can specify the topology via the number of chips. You don't have to specify this flag. If you don't specify this flag, what happens is GroqFlow does this kind of heuristic search where it counts a number of parameters in your model. It assumes all the parameters are in float 16, calculates how many, let's say, megabytes or gigabytes that might be, and it divides it over the SRAM capacity of the chips, which I believe is 230 megabytes. So it's a very kind of coarse heuristic. That's what we do in GroqFlow. So if things go wrong with the number of chips, maybe you have a no fit error, try playing around with this and just increase the number of chips. You can choose whether to rebuild your GroqFlow model. So I think Bill was talking about this before. The way he managed to get all of those examples running up and quickly is because he ran it before, and all the binaries and everything were cached. And if you want that to be the case, you can specify rebuild equals to always. And if you want it to compile every single time, you can specify rebuild equals to never. You can also specify your build name if you want it to be a bit more organized. And this is how you call your function on inputs. And this is not coming soon. There's actually an error. It's already there. You also have a benchmarking feature for GroqFlow. So you call benchmark on the Groq model, and it returns the average latency of 100 runs. You can also specify the number of repetitions. So that's an arbitrary parameter in milliseconds. And this includes the PCIe times and also the on-chip compute. So kind of an end-to-end example. We can also generate the Netron graph. So we talked about the Onyx representation. Onyx has another kind of third-party library called Netron, which allows you to visualize the compute graph, which you see over here. And you can interface, you can use Netron with the Groq model and see how your compute graph looks like. On top of that, we also have GroqView. I'm going to be showing you like a hands-on example about this later. And this is our profiling tool. It shows you the chip utilization and also shows you where all, let's say, the data elements are present on the chip at each individual cycle count. All right. Let me just go through some questions before going through the code example. There's a Groq.
There's a question, the Q&A window.
Yeah, I see it. Does the Groq API Groqit support all operations present in Keras, PyTorch, and TensorFlow? So we're trying to support as many as we can, and we don't actually target Keras, PyTorch, or TensorFlow. Right now, we target Onyx. I can show you the Onyx offset over here. So if you remember, we translate, I guess, your model representation in Keras, PyTorch, or TensorFlow into this Onyx representation. And this Onyx representation will have up to, I believe, 200 operations. And within Groq, I think we support most of them. There are some operations we don't support. So for example, non-max suppression. And that's because it's a dynamic operation and we work with static non-control flow type operations. So I guess the answer to your question is we support most of them and we're working to support more. However, there are some due to the limitations which we have right now, we're focusing on static operations. So non-max suppression, for example, wouldn't be supported. I hope that answers your question. All right.
May I ask a technical question? When you define the G model with Glock 8, you need to specify the input. So I guess that's to specify the maximum length. So does that mean if I change the length, I need to initiate this G model again?
Exactly. Yeah, you're completely right. Yeah.
I
And
see.
if you were to do that, I would also recommend you specify the rebuild flag. So what was it? This flag over here. If you specify this rebuild flag to never, even if you change the inputs, it's not going to compile again. So just be a bit careful with that one.
I see. So if I don't change the maximum length, I can use different inputs with the same G model, right?
Yeah.
I see. Thanks.
Mhm. Great. Thank you. All right, I'm going to go through an example. Can everyone see my screen over here?
Yes, I do.
Okay, great. Thank you, Marley. Okay, let me just try and move this. Okay. All right, so right now I'm going to show you an example of GroqFlow working. So before this build, walk through the proof points, and now I'm going to kind of walk through the point of view of someone wanting to port an application, what the steps you want to go through, and what issues you may face, and how you can kind of debug those issues. So let's start with a vanilla example. We'll start with a linear layer. So we do our imports. I'm going to work with PyTorch almost exclusively from now. So import Torch, import the neural network library from Torch, torch.nn as nn. And also I'm going to import this GroqFlow module. After that, I specify the model over here. So this is a linear model with input features of 320 and output features of 320. And I specify the inputs to be an input of dimension 320. Over here, I'm just asserting that the model runs and everything's okay. I get the CPU outputs is running on the CPU by default. And then I get the Groq inputs. Like I mentioned, it has to be in a dictionary format. So I specify the string, the name of the input. I also pass in the input with the specified data type, float32. Groq the function. I want to use the Groq view. I want to see how the Groq view looks like. So I'm going to specify this flag equals to true too. I'm going to want to use one chip. So I specify the number of chips. I'm going to specify rebuild equal to always because I'm going to change some of these parameters and see how things change. But let's just see how that works. So let me cd workshop. All right, so you can kind of see that running. You have your, I believe it's the CPU model last and then the Groq model first. And you can see the difference in the data type. The torch model is float 16, and I believe the CPU is float 32. And if you remember the presentation given by Andrew, it's because our MXMs have input as float 16 or int8, and also we quantize our Onyx graph into float 16. That's the step over here. All right, so maybe even at this point, I can talk about issues which might occur. So one issue which might occur would be that the weights in your file are not representable by float 16. So for example, what could happen, let me just use a contrived example, 1, 1, and then instead of torch random, I'll do torch tensor 1 to the minus, I don't know, 50. And let's see what that does. Oh, interesting. Well, we get different results. You can kind of see that on the Groq chip, we get 0.9185, and on the CPU, we get a different number. And that's because we're using different numerics on both sides. So if you have differences in outputs, you may want to think about how your weights are specified within your graph, and if maybe you can use float 16 or maybe you can't use float 16. If there are these edge cases where you do need, let's say, the dynamic range or whatever, float 32, something you could do is do quantization aware training, or you can also do like post-training quantization by passing in some samples and just kind of changing your weight such that this doesn't happen again. So that's one possible solution. All right. Now I'm going to change this back to the 320. And I'm going to go through the other features of GroqFlow. We're going to look at the benchmark API call. And over here, you can kind of see no inputs received for benchmark. That's because I didn't pass any inputs in. It's going to use these inputs that we specified while compiling the model. And it says that this is the end-to-end runtime, including PCIe and also on host compute. So 2.8 to the minus 5 milliseconds, which is pretty good. And as I mentioned before, we can go through MLAgility to actually benchmark this against other hardware. And as someone was mentioning before, we can kind of change the inputs, maybe increase the batch size and try and vary over that to increase throughput. And tomorrow, Chris is going to be talking about how to vary these different hyperparameters to increase throughput for scientific models. So stay tuned for that. I'm going to go through the neutron graph. Open in my browser. So as I mentioned before, the first step is converting your model into this ONNX representation. And this is how the compute graph for this ONNX representation looks like. It's a linear layer, so it's a matmul followed by an addition, or maybe like a generalized matrix multiply. It could be either of the two, it's the same thing, it's equivalent. And we see the model over here. We have an input of shape 320, gets passed into a matmul node. Right now it's expecting float 32 inputs and also weights. And is also expecting this addition to be done in float 32 as well. But of course, what happens is in our cache file, we can see all of these artifacts. So we have the float 32 base ONNX, we have the optimized ONNX, and we also have the float 16 optimized ONNX. So maybe let's have a look at how this one looks like. So it looks exactly the same input dimension, same intermediate dimensions, but what's changed is now it's got float 16 as the data types. So that's what's happened once we've passed this ONNX graph through the float 16 quantization and also optimization. In this case, you don't quite see the difference between the unoptimized and optimized graph, but in many cases you do, especially for more complex models. So just kind of reiterating what I did there, I ran the GroqFlow example, and then I went to the cache file. So it's in my home directories .cache folder and under GroqFlow. And this is the name of the application I'm looking at, or the name of the file I'm looking at, and the name of the file I'm running right now. I can see all the ONNXs right there. One last example to show you, and that is GroqView, probably the most exciting. So let me just run this again and look at the GroqView. Give it some time. Okay, device 0. So over here, we have our profiling tool, which we call GroqView. And we have a lot of statistics which we can gather from this. So maybe let's just look at the first thing we see over here. We see the utilization of all the different functional slices. So the application we were looking at, that was a linear model. So it's a matrix multiplied followed by an addition. The way this would be mapped to the chip would be we pass it through the MXMs, the matrix multiply units, before going through the VXMs, where you can do the element-wise multiply add. Sorry, element-wise addition. That's this over here. So we can see initially the memory slices are being used. That's probably because we're reading the data, the weights, and also the activations from memory. And we can see the MXMs on the Eastern Hemisphere after that are being used quite significantly, 80% utilization. So I assume that has something to do with the matmuls going on. And where's the VXM? VXM fairly low utilization, but I do think we use the VXMs later on, and we can see that in a different view. So this looks to be a memory-heavy workload, and that's great for us as well, because our SRAM allows us to have a lot of on-chip memory bandwidth concurrency. I think it's up to 80 terabytes per second of on-chip bandwidth. But let's go into another view. Andrew was talking about this earlier, that we have this deterministic scheduling. And at each cycle, I'm just going to pause this right now, we know where all the data elements are and in which functional slice they occupy and where they're going to. So you kind of see they're going to the MXMs to be multiplied. You can see how they progress throughout the execution of the program. This is a view of the chip. So you can see the VXM in the middle, the memory slices, SXM, also MXM. As you can see, it's symmetric along the vertical axes. And as these kind of data elements move across the chip, you can see this moving across time. But there's also another view, the container view. Oh, what's going on here? Schedule view. Sorry, I got the wrong view. Where instead of varying time, we set the y-axis to be the time axis, and we see how the elements move across the chip. So you can see here, these are all elements laid out in the memory slices, and we see them moving over to the MXMs and what happens to them after that. All right. I'm going to go back to the example and talk about debugging GroqFlow. So this is an example where everything works well. What about when things don't work well? Let me go to one of these examples. Okay, graph attention transformer. So what I have over here is I've instantiated a graph attention transformer. I've used very small features and very small dimensions. So it's a very small model. Specify the inputs and the parameters, put them in a dictionary, and pass them through Groqrack. And I've ran this command, and something's gone wrong. We look through the bottom here, and it's an Onyx export issue. So it says exporting the operator, let me just, A10 scatter reduce to Onyx, offset 16 is not supported. Please feel free to request support or submit a PR on GitHub. So this is an issue with Onyx itself. Now, there are multiple ways you can kind of get around this. Number one, what you could do is you could use Onyx script and write this operation in Onyx yourself, register a custom operation within PyTorch, and get that working. You have to do a bit of hacking, but I have an example I'm going to share in the GitHub repo for you to do. Something else you could do is you could try and rewrite your PyTorch script without this this operation. Sometimes it's possible, sometimes it's not. That's also another possibility. And those two are kind of like what you should be looking into. And of course, you can let us know and we can look into fixing this for you too. But just to let you know, this is an issue you might face, and it's an issue in the first stage of GroqFlow, which is exporting it to Onyx. Another issue you may have is, I have another example. It's non-max suppression. I was talking about this before and I had the question of, are we supporting all the PyTorch operations? So providing an overview, non-max suppression is an operation which is very commonly used in object detection. For example, in YOLO models, you would have non-max suppression as a post-processing step. Within YOLO, for example, you have all these bounding boxes at the end, and you want to create your final prediction. And for this, you use this non-max suppression block, and it's non-deterministic because it chooses the best blocks out of however many. And the number of these blocks may not be static, so things change over time. And that's something we don't work with right now, but we will in the future. So it's not something we support. And let me just go through an example of how GroqFlow will handle this for you. Non-max suppression. All right, so it says fail, see the whale, and it says your model contains Onyx operations that are not supported by the compiler, and also specifies the offending operation. Please replace these operations or just contact us. So in this case, there are different things you can do. Number one, like it says, you can replace the operation by another operation, or because this is like a post-processing step, what I'd recommend you do is you run everything else on the Groq chip, right? And then you do this post-processing on the host, on the CPU. That's something you could do too. So yeah, you have two options over here, well, three. Number one, you replace the operation. Number two, you break the graph, you do some heterogeneous compute, do some on the Groq system, do some on the CPU, you can pipeline and overlap the two as well. And number 3, just let us know and we will try and help you out too. All right. And now I have another example too, which is GPT-2, which was the example I had in the slides. And the reason I had this example is because I wanted to really stress on the need to specify the max sequence length. We work with static graphs and we want you to specify the max sequence length so that, for example, if you had smaller inputs, you just zero pad them and it will go through the compiler just as well. I can also run this example, PyTorch GPT-2. It's in the cache. I put it in the cache because it takes a bit of time to compile this. But of course, even if it were to take a bit of time, the benefit you get from having low latency inference is significantly more than that. And this only takes, I believe, 2-3 minutes of time. Okay, what does this say? BBC. I'm not entirely sure what's going on here. I think it's something to do with our runtime. It was working for me earlier today, so I'm just gonna probably do this offline and then send the example and make sure it's working. Okay, so that's kind of the examples I had for GroqFlow. The thing I wanted to do next was go through an example of us, not this example, an end-to-end example where we unpack all of the elements within GroqFlow. And for example, we have a data loader, we pass in elements through the data loader into our Groq model. But before that, maybe I'll look through the chat and see if there's any questions.
Sanjeev, there was one question that says, are there any provided suggested approaches for production inference serving over network sockets? Kind of comparing to NVIDIA Triton inference server.
Yeah, actually, I don't think I have an answer for you off the top of my head. This is kind of what we recommend to people, but we'll think about it offline and get back to you.
Yeah, Christian, we should have an answer tomorrow for you, if not by the end of the session.
Cool. I guess is that it, Brian?
That's all I can see right now.
Cool. All right, so the next step is I'm going to be talking about a ResNet 50 example, an end-to-end example, where in the end we have a model running on Groq, running through the entire ImageNet dataset. And we're not using GroqFlow in this case, but we're kind of decomposing GroqFlow and going through all the steps one by one. So let me just go through that. We do all of our inputs, all of our imports. We specify our transform. We're supposed to specify where we get our data and also the labels. So over here, I can show you where the data is, how it looks like, and data. Where did it go? I swear I had it before. Ah, it's over here. So as you can see here, we have our ImageNet example datasets. And for those of you non-familiar, ImageNet is like it's a well-known image classification competition dataset, and it has 1,000 classes, if I remember correctly. Yes, we have macaroons, rat. You can see a lot of different examples. And what we want to do is we want to pass through these examples through a model that's been compiled and also running on the Groq system. So to do that, what we do is we instantiate our model. We see that on line 69 over here. We instantiate this model using torch vision. So import torch vision.models as models, and then we import the ResNet 50 model from torch vision with the weights. I'm using the ImageNet 1K V1 weights. I assume 1K stands for 1K classes, and V1 stands for, I suppose, V1 of their training. And once we do that, we specify our dataset loader. And that's something I've done manually over here because I'm creating this this dataset class from a file, right? It's very much boilerplate PyTorch code. I'm not going to go into it right now, but we create this dataset. We create this dataset, pass it into a data loader such that we can kind of iterate through the dataset in a very efficient way. And once we have the model and also the data loader, we go through the steps one by one. So if you remember, we convert the PyTorch model into Onyx, and we use this torch Onyx export over here, where you specify the model, you specify example inputs, that's what you can see on line 73, and you specify where the model gets saved to. So that's the Onyx path over here, which I specify here too. Something else you could do is you could optimize your Onyx graph and then also quantize it to float 16. That's what you see over here. You can find this online. We'll also have examples in the GitHub repo after. So we're using the Onyx runtime API call. We input Onyx runtime here. We specify the graph optimization level. And we pass in the Onyx graph to be optimized. So once we go through all these steps up to line 90, we have an optimized Onyx graph. And then I pass it through the compiler with all the different flags. So I specify the topology. I say it's a 2-chip topology. I also have this compiler flag, which specifies that I want extra slices for instructions. And I also specify where I want to save this. So for those of you interested in going to like this level of detail, ANL has the documentation, so get in contact with them. However, what you could do as well, if you want to be cheeky, is if you wanted to, let's say, do a GroqFlow compile, let's go to GPT-2. All of the artifacts and the configurations are specified here. So you can see the compilation flags, the assembler flags, so on and so forth. And this is, yeah, so that's the exact assembler flag. You can also see the compiler flag. So you can use this as inspiration if you wanted to do this from scratch in this kind of system over here. And all you're doing is using the Python subprocess module, and you're calling the Groq compiler CLI tool directly. You could alternatively do this to Groq compiler, and then pass in, for example, your Onyx model. I'm not going to do that. Now, once you have compiled your model, you want to pass it through your assembler. And then after that, we have our runtime. So we use TSB runner. We create a multi-chip runner. We pass in our binaries. And we also specify the topology. In this case, it's a 2-chip topology. And then after that, we loop through our data loader, one input at a time. And it's only because while compiling this, we specified an input dimension, a static input dimension with batch size 1. This is something you can vary. This may not be the most optimal case. It's a real-time case, but it may not be the most optimal case. And Chris tomorrow is going to talk about how you may want to, for example, optimize over batch size and how you may want to do that. You can use GroqFlow to do that, or you can kind of interface directly with this and do it like that too. But let me just run this example. I'm going to comment out all of this because we've already run it. Base name. I think I might have. Give me 1 second. I commented out the base name. All right, and you can kind of see this running. And the reason I'm going through all of this with you is because when you want to run a real-time example, we avoid against using GroqFlow, only because there's a lot of overhead that goes into using GroqFlow. When you kind of have this logic for abstraction, we have a lot of, let's say, conditional logic, if-else statements, which slow things down during the runtime, during this kind of program execution. So what you could do is you could go through all of these steps one by one, or you could call GroqFlow on the model. And once you get your binaries, your IOPs, you call the TSP runner like this, and just pass in your binaries through there. That's what we recommend. So yeah, that's the hands-on session so far. What we've gone through is GroqFlow best practices. And if things were to go wrong, how you could begin addressing them. Of course, feel free to contact us and we'll support you as much as we can. We have our developer community on Discord, so feel free to join us there and contact us there too. I also went through kind of unpacking GroqFlow, going through an example where we export and do all the steps manually, and going through an end-to-end example with ResNet. And we talked about why you might want to do this, or at the very least use the multi-chip runner or the TSP runner while working on your scientific or whatever workloads, because GroqFlow introduces some overhead that we have to put in because of the abstraction. All right. I'm just going to cancel this because it's going to take some time. But that would conclude the GroqFlow section. So as a recap, GroqFlow is a wrapper around the Groqware suite that gives you the power to quickly compile and run models.